So during this session on say static inventory problems under uncertainty, I will be referring to two important issues. One is the Bayes criterion, and the second one is problem formulation with partial information. As you are aware, we have already mentioned that for this kind of problems, static inventory problems under uncertainty, in majority of the cases we will be dealing with partial information, and so the partial information related to the demand of the inventory item can be expressed in several ways. So during these lecture sessions, I will be referring to certain methods which you may apply to represent, or certain measures which you should be aware of, with which you will get an idea about the level of partial information. So this is very, very important, and our main focus is how to get these partial informations, or as many information as possible, relevant information as possible regarding the characteristics of the demand for the given inventory item. So let us the first discuss the Bayes criterion, how to use the Bayes criterion in this case. Now, I have already mentioned that there are three criteria, decision criteria you may adopt when the probability values are not there, but you have the payoff matrix. So only the missing point is the probability value. So in the payoff matrix, so you have to adopt some other means and to get a solution, and in this case we will just discuss the Bayes criterion. Bayes criterion is also known as the equal probability criterion. Now in this approach we assume equal probability for the all possible demand levels. That means equal probability, sometimes if it is a equal probability case, that means it is we are directly or indirectly referring to a particular distribution called uniform distribution. So just make a note that many a time when the probability distribution is not known, the starting point could be for analysis, it could be just to assume that the equal probability distributions or uniform distributions, and as you are aware that uniform distributions you can use for say the discrete random variable or the continuous random variable. So for both the cases you may use uniform distribution. So sometimes the uniform distribution is also referred to as the distribution with maximum ignorance. That means you are really ignorant of say the possible the demand levels in this case. Now here we are saying that if the probability against a particular demand level is not known, so why don't you assume for each possible demand, for all possible demand levels, the same probability. So that is the basic assumption. Now these assumptions may be questioned, but in many cases but there is a logic behind assuming equal probability for so each the demand level. So we will go by this logic. And what is this logic? That means if there are 4 possible demand levels, say 1, 2, 3 and 4. Okay, so these are the either 1 unit, 2 units, 3 units or 4 units. Okay, the probability of each demand level is assumed to be 0.25. That means when the exact probabilities are not known, let it be assumed to be the same. That means 1 by 4, that is 0.25. The basic assumption is when probability of a demand level is not known, we may assume that each demand level occurs with the same or the equal probability. That means that we are assuming that the frequency counts remain same for each event. When the probability value is assigned to each demand level, the problem under uncertainty is converted into problem under risk. And then what we will do, it's very simple. That means against each order strategy, you calculate the expected return or expected payoff, and either in terms of profit or in terms of the cost. So you select that particular order strategy for which the expected profit is maximum or expected cost is minimum. These two cases always we highlight. For the given payoff matrix, we are already are familiar with this particular payoff matrix. So 3 by 3 payoff matrix, 3 demand levels and 3 order quantities. So you have these tables. I don't need to explain it once again. So once these values are known, what you try to do, that means against each demand level is 1. Okay. So what will be your probability? There are 3 possible demand levels. So obviously for each each demand level, say 1 or 2 or 3, the corresponding probability will be 1 upon 3, that means 0.33. So obviously you write it here, the corresponding probabilities, so the probability against 1, 0.33, probability against 2, 0.33, and probability against demand level 3, again 0.33. So this matrix, the payoff matrix, is converted into a payoff matrix for the static inventory problem under risk. So the probability for each demand level is assumed to be 1/3 or 0.33. Already this point is highlighted. Calculate expected payoff for each order strategy. That means for order 1, obviously you say 3.5 into 1.3 plus 3.5 into 1.3 plus 3.5 into 1.3. So typical calculations we do for determining the expected the payoff. So it is 3.5. Similarly for the order 2, this is return 2.00 when the demand level is 1 and corresponding probability is 1/3. This is the return when the order quantity is 2 and demand level is 2 and the corresponding probability is 1/3. And similarly for the third the demand level, that means when the demand level is 3 units and order quantity is 2, the corresponding the return is 7 with a probability of 1/3. So the total is 5.33. So the same approach you follow for calculating the expected payoff, expected return against order 3. So this value is 5.50. So obviously the order strategy is to order for 3 units because 3.5, 5.33 and 5.50. So against order 3, the expected payoff is maximum, that is 5.50 in this case. Now, okay, so this is these 3 decision criteria already we have explained. That means the first one is the Wald criterion. You just check whether the Wald criterion is suitable in your case or not. If you find it is suitable, you apply it. If you find that it is not suitable, that means you don't want to want to adopt a conservative approach, so you may opt for the Savage criterion, that means the regret matrix, and then go for it and you get the solutions. But if you want to make the whole the system of taking or say determining the order quantity a simple one, our suggestion should be, why don't you go for equal the probability, the criterion, that means say the uniform distribution assumption. Okay, so that has been proposed by Bayes and the Laplace. Now, many a time what happens that this is the extreme situation what we have explained, but in many a time what happens that you are running say inventory control systems with respect to one particular inventory item, and then as you are say working with an inventory control systems, so obviously you are becoming aware of the levels of demands for the given inventory item. And as the situation becomes the stable, and so you can get an idea, or obviously you get an idea about the possible demand levels. Is it okay? So the first when you start the system, as the time passes, you start collecting the relevant data related to the demand of the given inventory item in a systematic manner, and so you will be building up this information base for the item demand over a period of time. So at any point in time, you may find that you will be dealing with partial information. It's not that at that point in time, at any point in time, suppose if someone asks you about the demand distribution or the type of demand distribution, you say that yes, I do not know what is the type of demand distribution, but I can tell you certain information related to the demand. Like I might tell you what is the average, what is the mean demand, or what is the standard deviation of the demand, what could be the possible the range, the maximum value, the minimum value. So many such the information you may have related to the demand. So this aspect is referred to as the partial information, and the first attempt should be that why don't you try to formulate the problem with whatever the information the given related to the demand of the distribution. So that's why we have named it problem formulation with partial information, this particular topic. As has been stated earlier, in the majority of the cases, information is made available about the characteristics of the demand. So the demand pattern, say, such as mean and standard deviation of demand. Is it okay? That means this may be known. However, with this set of information, it is not possible to conclude about the distribution of demand. You are already aware of. The question is, to what extent we can make use of this partial information to determine the order quantity. I hope that you have understood this problem. That means forget about the demand distribution now for the time being. Whatever the information you have collected, let this information be used to formulate the problem. Okay, and while you formulate the problem, obviously there could be certain say the criterion you try to the meet, and in majority of the cases you try to minimize the cost, or more specifically you try to minimize the total relevant cost. Is it okay? And the decision variable is known, that means the order quantity in this case. So in this context, the types of information that we may have as we start getting data on various characteristics of the demand are worth mentioning. So this the point we are highlighting now. Now you are all aware of a concept called moments of the distribution, moments, and so this partial information may be expressed in terms of the moments of the demand distributions. The students who are not aware of the moments of the distributions, so please refer to any textbooks on the probability and statistics, and just go through them, and I am sure that you will have proper understanding of the moments of the distributions. Okay, so again we'll referring to the basics of the moments of the distributions in this particular lecture session. In a given situation, we may know only some of the moments. Is it okay? So what are the common say the set of moments about the distribution, the demand distribution in this case, should be aware of. So how do you define moment of order R? Moment of order R, the notation is mu R, and Fy is the probability density function, Y is the demand, okay, or it is basically the continuous random variable. So the Y against Y, the probability density function is Fy. So it is integration 0 to say infinity y to the power r, because it is order r, Fy dy. This is the basic definition of moment of order r. Now the next extension of moment, that is mu r, is moment of order r around x. So the standard notation is mr dash, which is defined as integration 0 to infinity y minus x to the power r. That's why it is around x, y minus x to the power r, Fy dy. So this is the moment of order r around x. Now this particular x may be the mean, and the mean notation is z bar. Please note it down that we are using a notation z bar for mean. So moment of order r around mean z bar. So the standard notation is m subscript r, mr 0 to infinity integration y minus z bar to the power r Fy. The same definition we have followed, excepting x is replaced with z bar. So you call it moment of order r around mean z bar. I think it is clear. Next one is, next stage we go for say defining absolute moment of order r around x. So the standard notation is lambda r, lambda subscript r dash. So it is integration 0 to infinity absolute y minus x absolute to the power r Fy dy, because this is the absolute moment of order r around x, and this x could be the mean z bar. So if you want to have an expression for absolute moment of order r around mean z bar, okay, so this is the standard notation is lambda r, that is integration 0 to infinity y minus z bar absolute to the power r Fy dy. Now why we have the proceeded up to the absolute moment of order r around mean z bar. Now there is a reason for this one. You will find that to solve this kind of problem, that means the static inventory problem under uncertainty, that means with partial information, and with the help of distribution free analysis. So if you want to determine the order quantity in this case, now you are supposed to use, as the researchers have pointed out or have suggested, or a number of the inequality expressions, and these inequalities which you will find in the probability theory, these have been proposed by the great mathematicians in a situation where the exact form of demand distribution is not known. That means for any kind of distribution, these inequalities hold, or these inequalities are valid. So obviously in this case, when you are not aware of the type of distribution for the demand, so why don't you use any one or more of these inequality expressions? Now one important inequality expression is referred to as the Chebyshev's inequality. I repeat, this inequality is referred to as the Chebyshev's inequality, and this the Chebyshev's inequality has a close resemblance with the absolute moment of order r around mean z bar, that is lambda r. Is it clear? So I hope that this point has been made very clear, because you need to use, very soon you will come to know that for solving such a problem you will be say using many types of inequalities expressions. So, and this inequality, particularly the Chebyshev inequality and other inequalities also, has a very close resemblance with absolute moment of order r around mean z bar, that means lambda r. So that's why we have specifically the expression for the lambda r. Now, so with this information, partial informations, what we have the following relationships. First one is m1 equals to 0. You can compute why m1 is equals to 0. Okay. m2 is equals to mu2 minus mu1, that is the sigma square. It means what? That means it is essentially the second moment around mean. What is m3? m3 is mu3 minus 3 mu1 mu2 plus 2 mu1 cube. And what is m4? That means mu4 minus 4 mu1 mu3 plus 6 mu1 square mu2 minus 3 mu1 to the power 4. So I suggest that you as an assignment, okay, why don't you go to the basic textbooks on statistics, probability and statistics, and you get these expressions, okay, verified, right? So this is the first moment, this is the second moment, this is the third moment, and this is the fourth moment. That means suppose you have a situation where only the information up to the first moment is known. In many cases we come across such a situation. In many say the factories, in many workplaces, is it okay, whether it's the manufacturing or the service organizations, in many cases what we find that the data they are referring to, okay, that is only some average value or the mean value. In many cases even they just say that average is known, but if you ask them, sir, can you get me some idea about the variability or say the measure of dispersion, so they might not tell you anything. So the standard deviation, if you get the value up to the standard deviations of the variance, is it okay, it's one of the measures of the dispersion. So we might say that okay, the information is available up to the second moment, and as the situation, as the time passes and the system becoming more stable and all, so it is natural that you will be getting more the data about the demand patterns, demand distribution, and ultimately you may the compute the third moment with the given data set, and in certain cases you may also be able to calculate M4, that means the fourth moment. Now if you calculate, normally what we say that given a particular inventory item, as far as demand is concerned, suppose in a given situation in a workplace you find that you can get an estimate up to the fourth moment. You say that the maximum possible the data are so the volume of data or the types of data are made available. So up to say the M4, what we may conclude that if the data are made available with which you can calculate up to fourth moment, that is enough in majority of the cases. So this point you just keep in mind, and then we have the following relationships. That means M2R equals to lambda 2R. That means moment or even order moments Is it okay? This is the absolute moment. This is the moment, and this is the absolute moment. Okay. So what is the relationship? M2R equals to lambda 2R. That means even order moments when you deal with. And M2R plus 1 is less than equals to lambda 2R plus 1. That means for the odd order points, that means less than lambda 2R plus 1. That means absolute moment is always the greater than the moment of the distribution, and for the odd order moments. So these two relationships you just remember, and in a given running situation, as we have been referring to, the information up to third and fourth moments about the mean is quite common and made available. Okay. So this point already I have elaborated, and with this information the characteristics like skewness, the gamma 1, the skewness, that notation is gamma 1, and kurtosis, that the notation is gamma 2. I think you are already aware of a distribution can be measured. Now these measures are given by gamma 1, that is the skewness, that is M3 by sigma square, and gamma 2 is equals to M4 by sigma to the power 4 minus 3. Now minus 3, this particular value comes because of, say, the normal distribution. Now here one point you must keep in mind, that is, whenever you say that this is the skewness gamma 1, it means what? That means it is essentially whether the demand distribution is symmetrical or not, whether it is symmetric or asymmetric. So if the skewness is 0, the gamma 1 is 0, what does it mean? If the gamma 1 is positive, what does it mean? If the gamma 1 is say positive or some other values, okay, or say positive values or negative values, what does it mean? Similarly, the kurtosis means actually the pickettness of a distribution, pickettness. So many a time you say that I can calculate gamma 1, and when you get the value of gamma 1, you can get an idea about the shape of the distribution, and when you can calculate, say, the gamma 2, that means information up to M4 is available. So then only you can calculate gamma 2. That means the pickettness of the distribution also you can get an idea of. So these two are very, very important, gamma 1 and gamma 2. That means what actually you are referring to, that means first you start with M1, M2, M3, M4. Then first you check whether with the given data set calculation of M4 is possible or not. If it is possible, then what do? You go for calculating gamma 1 and gamma 2. So you will get a lot of information about the demand distribution. The expressions for absolute moment about the mean has a special relevance in this case. When we do not know distribution type of the demand, that is the case, that's why the problem under uncertainty, we can use certain expressions derived in probability theory applicable for any type of distribution. So that is the greatest advantage you have when you use these inequality expressions as given in the probability theory. The inequality of probability theory, known as Chebyshev's inequality, we can use for problem formulation, and this inequality expression resembles closely with the expression for absolute moment of distribution around its mean. That's why specifically we have referred to the absolute moment of distribution around mean. Is it okay? That is lambda r. And in the next lecture sessions, when you talk about the Chebyshev's inequality, So we'll get into the details, and you'll find that to what extent this is dependent on this particular the expressions for the absolute moment of a distributions. So I I close these sessions, and in the next sessions we will be referring to the Chebyshev's inequality. Okay, so thank you.